Welcome everyone to Algebra 2, Section 2.4, Complex Numbers. So for our warm-up, we are reviewing factoring. 1/2 x squared minus 8 equals 16. And actually, instead of factoring, I'm going to solve this one by square rooting. I misspoke a moment ago. We could factor, but we'd have to multiply the equation by 2 to make that a coefficient that's an integer, not a fraction. So in order to solve by square rooting, I'm going to get x squared by itself. So I'm going to add 8 to both sides. 1/2 x squared equals 24. Multiply both sides by 2 or 2 over 1. And we get x squared equals 48. From there, I'm going to square root both sides to get the square x can be by itself. So I get x equal to positive and negative square root of 48. The square root of 48 simplifies into the square root of 16 and the square root of 3. So it's really positive negative 4, which is the square root of 16, times the square root of 3, which would be our simplest form. Alright, so let's talk about the imaginary unit. This is going to be new to us, okay? So we've talked before, way back when, about real numbers. Now there's also such a thing as imaginary numbers, and we need to note that by I. So I is the imaginary number, and it's the square root of negative 1. And that's because you can't actually have the square root of a negative number. If you think about it, when we're saying the square root of a number, we're saying something times itself is that. So all of the things that we have that can be actual square roots are positive, because if you take two of the same number, whether they're like, let's say positive 3 times positive 3, you get a positive 9. But even if you take a negative 3 times a negative 3, you still get a positive 9. But if you were to try to take a negative 3 times a positive 3, that's still going to be, a negative 9, but you're not taking the same exact number anymore. You're taking a negative and a positive version, not the same exact thing. So it's not actually the square root. So that's why we can't take the square root of a negative like that. And so before we said, well, we can't do it. Now we're going to say why we can't do it is because it's imaginary. Now, if I is equal to the square root of negative 1, just our simplest negative square root we could have, that would make I squared whatever square root of negative 1 is squared. So if we go through and say, well, square root of negative 1, if we were to square that, the square and square root undo each other, and we're left with whatever's inside, aka negative 1. So let's simplify these square roots. The first one, square root of 9. Old classic, square root of 9, dropped my pencil there, is 3. Now, as far as the square root of negative 9 goes, we'd want to think of that as the square root of 9 times the square root of negative 1. Just kind of like we can think earlier, the warm-up, about the square root of 48 as the square root of 16 and the square root of 3. And that helped us say, oh, okay, that square root of 16 is 4. Well, this helps us because we couldn't simplify the square root of negative 9, but we can simplify the square root of positive 9. So we say the square root of 9 is 3, and the square root of negative 1 we're calling I. So we say the square root of negative 9 is really 3i. On letter C, we have the square root of negative 12. We'll do a very similar thing. We'll say, hey, this is the square root of 4 times the square root of 3 times the square root of negative 1. Well, the square root of 4 is 2. The square root of 3 just say square root of 3, and the square root of negative 1 is I. Well, we'll rewrite this, though, so the square root's at the end. So we want to do 2i times the square root of 3. So we like doing the number first, the regular number first, the 2. Then we'll do the I next. And then last but not least, we'll do any radicals. Okay, square root of 3 times square root of 15. So we'll multiply those together, get the square root of negative 45. Now as we have that, we say, well, square root of negative 45, that's the square root of 9 times the square root of 5 times the square root of negative 1. That helps us because we can separate out the I for the square root of negative 1, and we can deal with a positive square root of 9 and have 3. So that's 3I square root of 5. So once again, the 9 becomes a 3. The negative 1, square root of negative 1 becomes the I, and the square root of 5 just stays square root of 5. Now, one to ponder on, think through, is, okay, if I is equal to the square root of -1, then what do all of these other or subsequent powers of I end up being equal to? Well, I squared, we said earlier, is the square root of -1 times itself, which is -1. I cubed is really can be thought through as I squared times I. Because whenever you're multiplying with the same bases, remember the bases are the big part here, the i's, okay? So it's like if we were doing x squared times x, you'd have x cubed. Well, similarly, if you do I squared times I, you have I cubed, because you add those exponents. So that's the same thing as I cubed. So we can say, okay, well, it's I squared times I. Well, I squared, that's -1. And I is the square root of -1, but I'm just going to call it I still. And now, I cubed is really -I, because the -1 times I is just -I. Okay, well then I to the fourth, we can think of that in a few different ways. What tends to be the easiest is to think of it in terms of I squareds though, because I squareds are negative ones, and I'd rather multiply by that than by square roots of negative numbers. So we're going to say I to the fourth, that's really I squared times I squared. Well, an I squared times I squared is -1 times -1. So that makes I to the fourth +1. So now as we get to I to the fifth, we can think that in a few different ways as well. We could say, hey, that's I squared times I, because 2 plus 2 plus 1 for the exponents is 5. Or even simpler, we could say I to the fourth times I, because 4 plus 1. So if I have I to the fourth times I say, okay, well, I to the fourth is 1. That's not too bad. And I is just I, we'll call it. We could call it the square root of -1, but it's easier to call it I still. So that just ends up being the same I again. I to the sixth. Once again, we want to make it into as many I to the fourths and I squareds as possible, not necessarily I to the first, I to the thirds. Because we could technically call I to the sixth and write out 6 different I's, but that wouldn't be as helpful. We could say I to the third and I to the third, and that also might not be as slick, but it would still work. But the most helpful way to do it, the easiest way to do it, I should say, is trying to get as many I to the fourths and I squareds in these as you can, which is actually I to the fourth times I squared. So I to the fourth, well, that's just 1. I squared, that's -1. So 1 times -1, I to the sixth is -1. I to the seventh, that'd be I to the fourth times I to the third, because 4 plus 3 is 7. So that ends up being 1 times -I, is what I to the third was. So we end up just getting -I. Then I to the eighth, we can think of that as I to the fourth times I to the fourth, because 4 plus 4 is 8. So that ends up being 1 times 1, which is 1. So you might notice the pattern just kind of repeats. So we have I was square root of -1, then I squared was -1, I cubed was I to the fourth was 1, and then the pattern repeated. We had I, -1, I, 1. And that pattern is just going to continue on forever. So like I to the ninth would just be I. And I to the 10th would be -1 again. And I to the 11th would be I again. And I to the 12th would be 1 again. You just continue that pattern over and over and over again. So following that pattern, let's simplify the following. I to the 70th. So really what we need to think about is multiples of 4. Because every time you have an I to the fourth, you end up having just 1. That's what I to the fourth is. So any multiple of 4, whether it's 8, or I to the 12th, or I to the 16th, or I to the 44th, they'll all just be 1. So it's some multiple of 4 for the exponent. So a good, helpful way to do it is to actually take the exponent, 70, and divide by 4. So I'm going to take 70, divide by 4, and say, okay, 4 goes into 7 once, and we're left with 3. We have a 0 remainder, and 4 goes into 30 7 times, and we get 28 with the remainder of 2. Now that remainder of 2 is what we actually need, okay? So we can say that I to the 70th is secretly I to the, get this, 68th times I to the second. Now how did I come up with those two? Well, 4 times 17 is 68. The 2 is the remainder. So that's how we end up getting I to the second there. Now I to the 68th is just a multiple of 4, we said. So that really is just 1 times I squared, which is -1. So I to the 70th is secretly -1. Realistically, what you want to do, like I said, every time is try and see how many times 4 goes into a number for the exponent. So on letter B, we'll try the same thing. 33, and try dividing by 4 and seeing how many times it goes into it. I'm going to write mine a little bit lower. And I say, okay, well, 4 doesn't go into 3, but it goes into 33 8 times with the remainder of 1. So this is like I to the 32nd times I to the first. Well, that's just 1. I to the 32nd is, because it's a multiple of 4, times I, which is just going to be I. Go ahead and try doing letter C on your own. So maybe pause the video and continue on once you're done or are stuck. All right, so 99 divided by 4 is going to be 2 times 10 to the 9, and 4 times 10 to the 19 with a remainder of 3. So you end up getting I to the 96th times I to the third. That's 1, because 96 is a multiple of 1, or 4, 96 is a multiple of 4, whoopsie. And I to the third is just -I. So our answer ends up being -I. So you might be wondering, Mr. Kossel, do I really even have to be concerned with that first part, the I to the 68th, the I to the 32nd, and the I to the 96th? And my answer is not really, as long as you know it's a multiple of 4, because it's just going to become 1 every single time, because I to the 4th is 1, and the multiple of I to the 4th is 1. Adding and subtracting. So we can combine like terms, just like when we've done variables. Now, instead of making sure we have the same exponents and variables, we're going to make sure that we're combining real terms with real terms. Remember that W/ is my with symbol. Excuse me, I wrote real terms with terms. I meant real terms with real terms. So real with real is how we'll combine them. So let's write these following as a complex number in standard form. Now, we don't know what standard form is, so let's learn. Standard form is what we call A plus BI. Basically, the number without the I starts, and the number with the I ends. So here as we're combining, we have 3 is real, 8 is real. So we say, okay, well 3 plus 8 is 11. Okay, then the non-real, the imaginary, -5i plus 2i. So -5i plus 2i is -3i, just like you'd combine it with like x's. So now we have it in standard form because it's your 11, which doesn't have an I, plus, or in this case, minus your BI, which is 3i, the number with the I. And you can't combine those any farther because one of them is real and one of them is imaginary. Letter B, the tricky part here will be the subtraction. A lot of us can forget that we're subtracting this whole entire parenthesis. So what I always do, and I always encourage you to do, is changing this to a plus sign and changing these to the opposite symbol of what's there. Now as we combine real with real, we have the 4 and -2 give us 2. The 7i and the -9i give us -2i. and it's as far as we can go. We can't call it 0 because one has an I and one doesn't. One's imaginary, one is real. Go and try letter C on your own. Once again, this one has a minus sign. I'm going to change that to a plus sign and change these to the opposite symbols. Combining 8 and 11 gives me 19. Negative 5i and negative 4i give me negative 9i. Now when we multiply, we're going to distribute, or as we often know it called, FOIL. Now remember, as we're going through this, I squared is negative 1. It's going to be very important. Now, real quick sidebar, it would be very helpful for you to start to memorize the I pattern. That I is 1, I squared is negative 1, I cubed is negative I, and I to the fourth is 1. If you can remember that sequence, that'll be very helpful. But you can always continue to find it, just like we did up here when we actually went through and found that earlier. But remembering that pattern will be very helpful to you. So write these expressions as a complex number in standard form. Once again, that a plus bi form. So we're going to distribute 4i to these. So 4i times 5, just like we do if I was x, we'll say, okay, 4 times 5 is 20, and you have the I there. 4i times 2i is 8i squared, just like 4x times 2x would be 8x squared. Now we're not quite done though, because I squared, like we talked about, is negative 1. So that's really 20i plus a negative 8, because it's really 8 times negative 1. But now if we want it in standard form, you write that negative 8 first. So negative 8 plus 20i. On letter B, we have to FOIL here. 2 times 5 is 10. 2 times negative 6 is negative 12i. 3i times 5 is 15i. And 3 times negative 6i, or 3i times negative 6i is negative 18i squared. So now as I combine like terms, I say, okay, well, 10 is just 10. Negative 12i and 15i give me positive 3i. But this negative 18i squared is negative 1. So negative 1 times negative 18, positive 18. Now I can combine 10 and 18, and I want to write those first. 28 plus 3i. That way it's in my standard form for a complex number. So my answer is 28 plus 3i. Go ahead and try letter C on your own if you haven't yet. On letter C, we'll do 2 times 2, get 4. 2 times negative I, negative 2i. I times 2, 2i. And I times negative I squared. Combine like terms. 4 stays the same. Negative 2i and positive 2i go to 0. We do not have to write plus 0i. We do not write plus I. We say, nope, nothing there. We say, okay, well, negative I squared, that's secretly a positive 1, because negative I squared is a negative times a negative 1. So now if we do 4 plus 1, we say, okay, well, that's 5. For all of this to be the beginning, ended up not being too bad. All right, now dividing these. We're going to multiply by a number equal to 1, just like we have been with anything. So just like when we've been doing radicals, and we've been saying, okay, we'll multiply the top and bottom by the square root 3, or the square root 2, or the square root 8, or whatever, we're really multiplying by quote-unquote 1, because it ends up being something divided by itself. In this case, it's going to be like I over I, or something like that. Because we don't want an imaginary number in the denominator, just like we don't want radicals in the denominator of our final answer. So this instruction is for the next page. Write the following expression as a complex number in standard form. So 3 plus 2i over 6i. We can't just divide these straight up because we have addition in the numerator. But we don't want the I in the denominator. We don't want an imaginary number down there. We only want imaginary numbers in the numerator if possible. Or actually, it's always possible. But so we'll multiply by I over I. And why that'll work is on the bottom, we'll get 6I squared. And if you notice, the I squared is going to become a -1, which will make this work. On the top, you have to distribute and get 3I plus 2I squared. So on the bottom there, that 6I squared is really -6. On the top, that 2I squared is -2, because 2 times -1, just like on the bottom, 6 times -1, plus 3I. And we still can't reduce because we have addition on the top and bottom. Now, we said we want it in the standard form here, okay? So we're actually going to split this fraction up into two different fractions. So I'm going to write that down here, and I'm going to do -2 over -6 plus 3I over -6. So I just split this numerator each over the denominator. Now I can actually reduce the -2 over 6 to 1/3, and the 3 and the -6 for the I, not plus, minus, because this minus symbol, or negative symbol, to I over 2, or 1I over 2, if you will. So you end up getting 1/3 minus I over 2. A quick recap on this one, as we did a few more steps. We had to say, okay, well, we can't reduce the start. What we can do is say, well, I don't like this I here on the bottom. So I multiply the top and bottom by I and I, just like when we did radicals. Then we distribute on the top and we say, okay, we get 3I plus 2I squared. On the bottom, we get 6I squared. So the top, the 2I squared, that's 2 times -1, because that's what I squared is, and you get -2. On the bottom, we have 6 times -1, because that's what I squared is, and you get -6. Then we said, well, we want it in our standard form, which is A plus BI. So we want it split up, not as part of one big fraction. So we put them each over the denominator. You got -2 over 6 plus 3I over 6 coming from this part of the numerator and this part of the numerator. -2 over -6 was 1/3, and 3 over -6 was 1/2, but you saw the I, so it was I over 2. Letter B might be a good idea to try this one on your own. All right, I'm going to multiply the top and bottom by I again, because once again, I do not like that the denominator has an I in it. So we get 4I plus 9I squared over 12I squared. On the top, 4I stays 4I, but I'm going to write that second, because 9I squared becomes -9 plus that 4I, because you have 9 times -1. On the bottom, 12I squared becomes -12 when you have 12 times -1. Now, to put this in standard form, A plus BI, I'm going to split the numerator into -9 over -12 plus 4I over -12. Now I'm going to reduce -9 over -12. 3 goes into both. -3 goes into both to give me 3 over 4. 4 over 12, 4 goes into both, give me a minus 1I, or just I, over 3. And now it's in my standard form. All right, last 3 problems here before we have a Calvin and Hobbes comic. Solving a quadratic equation. So x squared plus 25 equals 0. This is a bit of a throwback to a solving by square roots. You might notice you can't factor this one, actually, though, which is why we have to do square roots, because this is plus 25. If it was x squared minus 25, that'd be a difference of 2 squares. Rather, though, we'll subtract 25 to get the squared term by itself, and we'll get x squared equals -25. Now we have to square root both sides, and you might notice, oh, x equal to positive negative square root of -25? What is the square root of -25? Well, we know the square root of regular 25, so to find the square root of -25, we say, okay, well, that's the square root of 25 times the square root of -1, because we can just multiply those two together to get -25. That's helpful because we can say the square root of 25 is 5, the square root of -1 is I, so it's positive -5I. Letter B, same idea. We'll start out by dividing by -6 to get the squared term by itself. So we'll get u plus 5, in parentheses being squared, is equal to -20. From there, I'm going to square root both sides because the squared term is by itself. U plus 5 is equal to positive and negative square root of, and I'm going to actually start breaking this down a little bit. 4, square root of 5, and the square root of negative 1. So whenever you have a negative, I'm always going to make one of these square root of negative 1. And we're going to start having 3 of these at times, unless the actual number is a perfect square, in which case on the last one you just had 2 radicals. This time we have 3 of them, because even though 5 isn't a perfect square, 4 is. So now, before I subtract 5, I'm going to clean up my right side. Square root of 4 is 2, the square root of negative 1 is I, and the square root of 5 is square root of 5. Now I want to subtract 5 from both sides, and remember I like to write that first. So u is equal to negative 5 plus or minus 2 times the square root of I times the square root of 5. We cannot combine those and call it like 3i or negative 3i, because 5 is not multiplying with that square root of 5 like 2i is. And that is our final answer, because we can't combine the real number, negative 5, with the imaginary number, 2i. Last but not least, letter C. 3x squared plus 10 equals negative 26. I'm going to start by subtracting 10 and get 3x squared is equal to negative 36. Divide by 3. X squared is equal to negative 12. Square root both sides. X is equal to positive negative. Once again, I'm going to start simplifying here. Square root of 4, square root of 3, and square root of negative 1. That's helpful because the square root of 4 is 2, the square root of negative 1 is I, and the square root of 3 is square root of 3. X is by itself, nothing more we can simplify. We solve that equation as much as we can. Positive negative 2i times the square root of 3. Alright, here's a Calvin-Hobbes problem that isn't super crystal clear, but we'll talk about it anyway. So you see Calvin here. Here's another problem, math problem I can't figure out. What's 9 plus 4? Love this one. Oh, that's a tricky one. You have to use calculus and imaginary numbers for this. And you see Calvin over here freaking out like many of you probably are at this moment about imaginary numbers. And then you start talking about some other imaginary numbers. 11, 13, 12, those different ones. And it's all a little confusing. And how did he learn this? Never gone to school. He's like instinct, tigers are born with it. So thankfully those aren't the imaginary numbers we have to deal with, because I wouldn't quite know how to add 11 to anything. But I can deal with some i's. All right, that is the note today, plus a little comic. Sorry for the blurriness of it. Oddly enough, I think it was clearer before I zoomed in. So right there, it's a little bit better. I should have left it like that. We could have read it way better.